Testing, testing. 1, 2, 3. Alright, so sorry for the drought. We've been forced to my apartment in order to record some lectures. We've had some issues with conference rooms, and so I've been giving the lectures themselves to my students in the actual conference room itself, but haven't been able to record. So this is me going back and recording for all of you online to make sure that you guys get access to these lectures as well. So thanks for bearing with me, and let's go ahead and get started. So last time, if you remember, we covered ideal and conceptual measurements again. We went through range and ideal range and ideal range rate, and we talked about azimuth and elevation. Today we're going to include simulating observations, and I'm going to show you a little bit of how that ends up happening, or what ends up occurring for simulating observations. Because really now we're starting to get into the real part of orbit determination, and I kind of alluded to this last time, but you know, even though we're simulating observations, we're still starting to talk about observations minus our computed the state, right? So we observe the state and we subtract it from our computed state or our model, and that gives us some residuals. And really what we want to do in orbit determination is we want to reduce our residuals in order to give us a better prediction of what the state's going to be, right? Or what it has been in some cases. So ideal range, remember, we're ignoring the propagation. It's literally the geometric range at that time, so the difference between position vectors. In the case of, you know, so long as the two position vectors are in the same coordinate frame, the difference is going to be the same, because it's a magnitude of that difference between the two position vectors. So it's going to be the same so long as those two position vectors are in the same frame, which they should be if you're subtracting them anyways. So, and how do we account, since this is geometric range and we're looking at some ideal observations simulating them, how do we account for propagation? For instance, like a laser rangefinder, right? We need the speed of light times 2, and that's going to be the time when it returns, right? So we have to figure out when it actually hit the observed target, and so on and so forth. Well, we include those errors in, as you see, our observed range is just going to be our geometric range plus some error, right? Same thing with range rate. Range rate is, remember, is the relative velocity in the direction of the range, and so it's the error, because we're, you know, doing this instantaneously, and the propagation is included in our error. So azimuth and elevation, right? So that xt and those rt's, you should know what that subscript t is, right? So, or at least have an idea of what it's indicating. It's topocentric, right? So as we go to our ground stations here, right, so topocentric frame is at those two ground stations, which we'll get to in just a sec. Don't worry, I'm not skipping ahead yet. The topocentric frame is at that point, it's fixed on the surface of the celestial body. In this case, the Earth, and at one of those two ground stations, right? That would be a topocentric frame. And so we have our elevation and azimuth from the coordinates in those frames. And so elevation is actually, you can think of it as our top down, right? So our, if I can put my hand in the camera, you know, it's as I'm looking out across the horizon and I start to tilt my head straight back up, right? All the way from one end of the horizon to the other. And all azimuth does is the angle from north, right? So which way am I facing, and how high up am I looking, right? So elevation is how high up I'm looking, and azimuth is which way I'm facing. It gets important because obviously you can't see a satellite below the horizon if you're on a ground station. So you can use an elevation and an elevation mask to determine whether or not you can see a satellite. And so we'll cover that in just a second. So for right now, I'm using some of the examples in the book, specifically the initial section of the chapter where we start talking about simulating observations. So we have some set of initial conditions that, in this case, that we consider the truth, and some perturbed conditions, which are our observations. Using geometric range and range rate, we're going to use our two sites, Easter Island and Fortaleza, Brazil. Obviously, Fortaleza, Brazil is on the right-hand side, or more easterly than the Easter Island. And as you're looking at the ground track there, this is done in MATLAB, by the way, you can actually see that the ground track, the first pass passes directly over Easter. Excuse me, the first pass passes directly north of Easter Island, and the second pass passes directly overhead over Easter Island. So Easter Island is going to get a pretty good look at the satellite coming overhead, in this case the Space Shuttle initial conditions that the book continues to use. But Fortaleza is really only going to have one good look at that Space Shuttle as it's coming by, and that we can attribute to our elevation, right? So our elevation mask, like I was saying, we can use to determine whether or not the Space Shuttle is seen. And so what that means is, so if you walk out of your house or conference room or office right now, maybe even look out your window, right? You can't see all the way to the edge of the horizon. There's a tree, there's a building, there's something in your way. And all the elevation mask does is it says, okay, from 0 to 5 degrees, or from 0 to 10 degrees at this azimuth, or this way in this direction that I'm facing, I can't see the satellite because there's something in my way. And so in this case, the satellite's below the horizon for pass number 1. It may be within that 0 to 5 degree range, but there's a pretty good chance that if we're looking out from that ground station that there's going to be something in our way, and so we're going to get a very poor pass. So this is the geometric range from our Easter Island and Fortaleza. I did this in MATLAB, and I did this all the way out. So as you can see, we have a minimum when the satellite starts to approach the ground station. But look at Fortaleza for a minute on the left-hand side. It doesn't even break 2,000 kilometers. Whereas Easter Island, that first pass is well under 2,000 kilometers. So we know that we're going to get a much better look at Easter Island. And so this is one of the things where we start to kind of judge the observations that we see. So if we were to use that first measurement, right, from Fortaleza, that's not necessarily a very good observation, right? It may be a very poor observed range that we get returned to us because it's either in that elevation mask or very close to it, right? It may not be, so it won't even be overhead on the horizon very long. And so I'm going to show you some horizon charts or some sky plots in the next lecture. But for right now, we're just going to use the range all the way out. And so I went up to about 12,000 in order to make sure that we got the two passes that we saw to replicate what was happening in the book and kind of give you an example for class. So anyway, so this is our computed range. So this is from the nominal state, right? So this is what we assume that the satellite started off with, and then we propagated forward using the J2 perturbations. Okay? So propagating forward using those J2 perturbations, we get our computed range, which is just the difference in the position vectors, if we remember right. And then we find some range residuals. So points to whoever can tell me what's currently wrong with these range residuals. Now I'll give you a hint here because without context, you're never going to guess. I used ODE 45, right? So let's think about that for a minute. Okay, so ODE 45, so it's a numerical integrator. It's Runcutt-Feldberg, right? But if I only used the initial time and the final time, it uses a variable time step, right? So if it uses a variable time step, and I remember, because we're simulating observations here, so not only did we propagate our initial nominal state, so our computed state, we also propagated forward our quote-unquote real state, which was perturbed, right? But if I propagated both of those separately, and I just took the output and subtracted the observed minus the computed, what are we going to get? We're going to get observations in computed observations that are not lining up time-wise. So time, our independent variable, we have to be very precise with this, and this is where timing precision comes into play here, because so a satellite passes overhead, right, and it reports its state based on the best clock that it has. Well, it's an orbit, so there are relativistic effects. It has to have a good atomic clock, right? If we're using an atomic clock, maybe there's only an oscillator because it's a university CubeSat. Well, did it determine it from GPS? What time are we using? The better the precision of the independent variable, the better we can determine the residual, right? So in this case, because the times don't line up, that's not a true residual. This is actually incorrect, right? I mean, we can use it, but it's I'll show you what happens when you actually use the time all the way out, like the real time lined up, not real time or correct time. It would just be the time lined up, excuse me, and show the residuals. And you'll see that it, you may get the general properties, but you're missing quite a bit. So I think I've covered pretty much all that I want to cover with the range residuals here. The important part, I've made my point that you need to be cognizant of the independent variable time, especially when you're differencing your observations from your computations, because you're trying to reduce that residual. So let me show you some of the output of the code real quick. Bring MATLAB over here real quick. So, yeah, example 3241. So this starts on page 95 of the textbook. So if I were to run this real quick. Sorry, I was trying to mess with some of the timing here. So let me make sure. Line 77. Excuse me. Oh. Oh, sorry about that. I was trying to show you guys the sky plot, and I forgot I hadn't actually finished it. I just kind of left it undone. So let me go ahead and run this real quick, and we'll show you the output. Show you the ground track, and we'll show you the range, the geometric range, the plots that you just saw again, as well as the residuals. And this time it's the real residual, right? So here's our computed range from Easter Island. Again, we dropped below 2,000 on that first pass, so it's going to be hard from Fort Azalea to really say that this is a good observation. So this is another thing why, this is another reason why orbit determination, you need to know orbit determination, or at least be able to transfer between different frames when you're considering where your observations are coming from, because you need to be able to select the right ground station. And so here are our range residuals, right? Well, let's look at the PowerPoint real quick. But correct me if I'm wrong, there's some behavior here that's not captured, right? So we actually continue growing quite a bit all the way up till 4,000, whereas in the other one where the time's not lined up, we fall. So clearly, we capture that there's a periodic behavior, but I mean in the real one, that's not even, the behavior is not matching. So you need to make sure that your independent variable is correct, and that you're calculating it precisely, whether through the use of an atomic clock, a maser, a very good oscillator because you're on the ground and you don't have to worry about heat so much. Whatever it may be, you just need to make sure that your time lines up in order to get the correct residual. And so let's look at this in real life for a minute. as you can see here, this is the SatNOGS network. Now, SatNOGS is an open source software and hardware network of ground stations. We're finishing up one here at the University of Alabama. Hopefully, we'll have it done by the end of March and up and installed on the Aerospace Engineering and Mechanics building, Hardaway Hall. Still working on it. It's still in testing mode right now. It's actually deactivated because somehow observations started getting scheduled even though we were still in testing mode, so we unplugged it as we finished our build because we were running it. And at the time we left it up because we were running some tests as far as network accessibility and things like that. So anyways, so let's look at the network real quick, right? So you can see all of these ground stations scattered throughout the world, right? There's one out there, there's one in Portugal, there's quite a bit in the US, primarily around the coastlines. There's quite a lot out in Europe. There's even one in China, there's one in Japan, there's a few in Australia, you know, South Africa, right? There's a whole bunch. Okay, point being. So if we take a look at our observations real quick, let's pick one that's already been done. Oh geez, there's a lot scheduled. Yeah, geez, man. Demetrius is kind of scheduling a lot of observations. Okay, I'm just going to go to mine real quick. Alright. So this is Fox 1D satellite. This is an amateur satellite. We scheduled an observation with a ground station here out in, I believe this one's in Britain. Yep, this is the one out in Britain. Okay. So, let's take a look. So, you know, there's a sky plot. It's called a polar plot for SatNOGS calls it a polar plot. But as you can see, it starts in the south, goes across to the north, right? And so the rings are elevation, and then your azimuth is obviously where it's heading. So, and it, you know, rises at 148 degrees azimuth, and obviously sets at 350. This has a elevation mask of 5 degrees, if I remember correctly. And so this was VHF, right? So this is an amateur radio. Well, let's look at the waterfall plot for a minute, okay? So you can see, we're scrolling down these sharp lines here. These are the frequency. This is supposed to be the satellite right here, right? And so it looks as though it's almost dead on, but really our sound is coming from here, right? So this may be some echo, there may be something going on here, but let's assume for a minute that these, just for the sake of argument, to make my point here, that these sharp lines are, these strong lines are the satellite, okay? So if these strong lines are the satellite, there's a wave that occurs as it passes overhead. And as it passes overhead, we see a Doppler shift, right, which is the range rate, or directly provides our range rate because it's the relative velocity change. And it's not down the center. So if you look, it ends up at -10 and shifted inside of 10. So if it's not directly on 0, because this is a centered frequency, then the TLE used, the two-line element, right, which provides us with all of our orbital elements, drag terms, you know, everything we need to propagate forward in time, then our TLE might have some error that we have to account for. So in other words, our observed won't match our computed from our TLE. And so this is an example of it in real life here. One of the things that I'm actually working on right now is making sure that that track down the middle actually is the satellite, because if this is the satellite rolling down through then what's with the ghost frequencies that are happening? You know, like it's a little weird, and so it's something that we want to figure out on our own, especially since we're putting our own ground station up as to what's actually occurring here. And so here's another one here where you can see that, I mean, the line goes straight down pretty much, right? But we still see some curves out here, which maybe they're the Doppler shift, we're not sure, you know, but this doesn't show waves because, and so these bars out here are frequency and some data coming through, but the straight line coming down the middle is because the TLE was computed accurately enough that the observations don't show a significant deviation, right? Because if it was a significant deviation, then we would see this straight track actually deviating a little bit and showing that Doppler shift, that ghost track that you see kind of following along on the left-hand side there, right, where there's a shift about the middle as it passes directly overhead. So I think we've covered most of what I wanted to cover for today, for Lecture 8. You know, I'm going to post this, and then we're going to roll through. I'm going to go directly to Lecture 9 right after this, make sure that that gets posted, and send them all out to you, since we've had some issues with recording. So, hope you enjoy this. Thanks for being patient, and I look forward to seeing you next time.